All right, so I'm very happy to introduce Professor Andrew Jordan as today's IQuest speaker. Andrew received his BS in physics and math from Texas A&M, then his PhD in theoretical physics from UC Santa Barbara. He did his postdoc at the University of Geneva, followed by a stint as a research scientist back at Texas A&M before starting as an assistant professor of physics at the University of Rochester in 2006. Andrew was ultimately promoted to full professor at Rochester and remains a research professor and group leader there, but very recently moved to Chapman University in my home county of Orange County, California, to co-direct their Institute for Quantum Studies. And Andrew is well known for his work in the theory of quantum measurement and related topics, and I know that he's a friend and frequent collaborator of at least a few IQuest members. So please help me welcome Professor Andrew Jordan. Go ahead and take it away.
Okay, thank you so much. It's a pleasure to be able to address your institute and to be able to at least visit you virtually anyway, if not in person. So let me go ahead and share my screen. Here we go. All right, so hopefully you're all seeing that now. Good. Well, usually when I'm talking with my friends in Illinois, like Paul and Gina and colleagues, we're talking about quantum opticsy type things. And so we're talking about maybe weak value amplification, or recently we're talking a lot about quantum telescopes and how to do opticsy things. So I thought it would be fun to mix it up a little bit and talk about a different topic entirely, which is another one of my interests I've been active in recently, which is this area of quantum measurement engines. So it's something that we're working on and excited about, and I wanted to share it with you today. So indeed, I'm at the University of Rochester, but again, I've recently moved to Chapman, and much of this work is funded by the Department of Energy, and then recently also by the Templeton Foundation. So the basic idea here is that if we remember our undergraduate thermodynamics classes, there is this whole discipline of thermodynamics that tells us how heat and work play off against each other, and we can use our understanding of these quantities to build things like steam engines. And so the idea is you have some working fluid like a gas and a piston, and then you have some hot and cold reservoirs. The hot reservoir could be maybe prepared by burning some coal in a fire. And we take heat from this hot reservoir, we use it to do some useful work, W, and then put some some heat into the cold reservoir. And in this way, we can create useful engines that we still use today for all kinds of different things. And so this is the basic idea. In the past several decades, people have been very interested in taking this working fluid here, this, for example, gas or what have you, magnet or what you like, and replacing it with something very small, it's like a quantum system, and then trying to see how our understanding of thermodynamic laws change under such circumstances. And so this has been a very active and interesting field. It's really picked up steam, pardon the pun, the past few years, and people are very interested in this kind of work. And so people are doing this. And I've been working in this too, but the field always seemed a little bit funny to me, because we're taking these exquisitely designed quantum systems like these superconducting qubits or these cold atoms, where we work like crazy to make this beautiful control over all of these nice quantum systems. And then we put a flame under it, essentially, to see how it reacts and be able to make it move in some funny ways. And so this is great for understanding thermodynamics, but I thought somehow from a technological point of view, it's a little bit stepping backwards. And so my friend Nicole Younger-Halpern sometimes calls this quantum steampunk, because it's sort of like futuristic, but also kind of antique at the same time. And so what I want to tell you about today is something a little bit different. What I want to do is I want to get rid of those thermal reservoirs, because one of the issues we run up against is, even though you have this very fancy quantum system here, when you figure out things like the efficiency of this engine, we know here, back in the classical days, the efficiency is bounded by the Carnot efficiency related to the temperatures of these hot and cold baths. Well, it turns out that basically with quantum systems, efficiency is also limited by Carnot efficiency, maybe a few claims to the contrary, but most everyone recognizes the Carnot efficiency. We're stuck with that. And so one of the motivations we have is if we get rid of these reservoirs, the hot and the cold, maybe we can get around this Carnot efficiency bound and do something genuinely new. And so that's the challenge for today's talk. We want to throw away this Boltzmann constant and really double down on our H-bar to see if we can replace this field of quantum thermodynamics with our newly created field, which I like to call quantum energetics. It sounds something like a startup tech company or something like that. So this is the subject of today's talk. And I want to design a fully quantum engine with no, for example, here's a motivating question. Can I design a fully quantum engine that operates with no work done by some system Hamiltonian? All right, so that's a secondary sort of challenge that we can have to thinking about. So here is the basic idea. We can think about an analogy when we start doing quantum measurements. If we introduce measurement into the story, measurements play a dual role in quantum mechanics because on one hand, they randomly perturb the state of the quantum particle, but they also give us information about what's going on about the quantum system. So they play this dual role. And if we think about measuring some quantity of the quantum system that does not commute with a system Hamiltonian, it's easy to see that non-commutation implies that we have to have some kind of fluctuation of the system energy in the process of measurement. And this stochastic change of energy is analogous, you might say, to heat in a thermodynamic context, because on one hand, we can't predict it or control it. There's some random fluctuation of energy. So there is some analogous heat-like thing in the theory of quantum measurement. And so Alexei Ofev, my collaborator and friend, likes to call this quantum heat. And the idea is you might think this quantum heat is just some random, like a vacuum fluctuation or something like that, so we can't do anything with it. But in fact, that's not true. We can find ways to rectify this quantum heat and pull it out of the system, just like a heat engine does, to be able to use this seemingly random source of energy in a directed way to do useful work. Okay. So I want to give some little examples right off the bat just to show you how this works. So I'm going to start with an example I came up with my postdoc at the time, Cyril Elward. And the idea of this paper we published in 2018 is to try to use this quantum measurement process to build some tiny hyper-efficient engine using measurement as the basic energy source. Okay, so this is the idea. And let me give you kind of a cartoon overview of what we're going to be talking about. So this is the schema for all these measurement engines I'll be talking about with you. We have a quantum system here on the left. We do some kind of measurement to this quantum system. The details of that we'll talk about later. It'll turn out we actually have to fuel this apparatus. We can't just let it do its own thing without some fuel. We have to give it some energy. That measurement tells us something about the quantum system, but also squishes it a little bit. It gives some disturbance. And the idea is that the difference from that disturbed state and the original state gives us an opportunity to pull some useful work out of that quantum system. We then have to generally do a reset process where we go back to the original system, and that establishes the original configuration, and that provides our cycle. So this is like our work engine cycle that we'll be expanding on in the rest of the talk. But that's the schematic example. So I want to start with a very simplest example to sort of convince you why this is interesting. And it's something that's easy to understand. So here is the simplest quantum system, a two-level system. We'll give the, say, E some energy, say epsilon over 2, and the ground state some energy minus epsilon over 2. And now we can imagine, suppose that I prepare the system in the ground state. So the system is just sitting here minding its own business in the ground state. It would stay there forever if you didn't do anything to it. And now what we do, we're going to come along, and if I measure that system, say in the ground excited state basis, well, nothing much of interest happens. I find out it's in the ground state, but the post-measurement state is exactly the same as the ground state, and so nothing changes. There's no nothing energetically interesting happening. And that's because I'm measuring in a basis that commutes with the system Hamiltonian. But now suppose I do something different. What if I measure not in the EG basis, but in the block sphere picture, I measure in some different basis, we'll call it the plus minus basis, consisting of E plus or minus G. What happens then? Well, now something interesting happens. No matter which outcome you get, either plus or minus, if I look at the expected energy of those states, the expected energy is epsilon over 2 for both of them. So before I made the measurement, I had energy, say minus, in this notation, minus epsilon over 2. After the measurement, I have energy 0 in this convention, and so somehow I've gained energy on average epsilon over 2 by doing this measurement. Okay, and so this is somehow the interesting feature of this example, that I seem to have created energy from nowhere. Right? I started with minus epsilon over 2, I ended with 0, so I gain this epsilon over 2 of energy. No matter what outcome happens, either plus or minus gives the same thing. So you can say, where does this energy come from? I didn't just create it from nowhere. We believe in the conservation of energy in physics. And one of the things that you can show is that in order to do this measurement, you have to have some energy of the meter that you're using to measure this two-level system with. So that's something interesting that comes into this story, is that when you read your quantum mechanics textbook, it just says do a measurement. But one of the things we learned from this research is that no, you have to have some resources to do a measurement. Otherwise, it simply won't work. And so what you can do to make a cyclic engine out of this is that you can have a memory, and whether you can tell it whether it ends up either with plus or minus. And then depending on what I do is, if I say plus, then I can apply a pi over 4 rotation to rotate the state plus back down to G. And in that process, I can extract that energy by transferring the energy of the qubit to some, for example, optical pulse I send down to interact with it. Or equivalently, if I find it's in the state minus, I can send a minus pi over 4 pulse to be able to come down and extract the energy that way. And so using this, I can then create a cyclic engine where I'm transferring energy from the measurement process to this pi pulse control tone that I use to extract the energy with. Okay. Good. Now, maybe some subtleties that I should mention here. So this is a little bit reminiscent of some of the work done back in the thermodynamics foundations community about whether you can create, for example, a single atom heat engine using thermal reservoirs. And one of the lessons we learned from that, from following Bennett, Landau, or Szilard, is in order to make a thermodynamically complete story, we should also worry about in the context of a Maxwell demon, we should worry about the memory of this demon. So in order to make a thermodynamically complete, we should then maybe erase this memory so we don't have an infinite amount of energy or information being stored. Okay, so this is also something that we can talk about. And then something also happens very interesting is that I can have a no feedback version of this if I rotate the state psi, say just below plus. So rather than starting it in G, suppose I started it in a state just below plus, that still has energy less than plus, but because of the close angle between the state and plus, by the Zeno effect, I almost always get plus if I measure in the plus minus basis. And so I can have a no feedback limit in the case where I have very small amount of energy I extract for each one of these measurements.
Andrew?
Yes.
Paul has a question.
Go ahead, Paul.
Hi, which I actually just also put in the chat. So the question is whether or not at the end, if we stop in the middle of your process where we've measured either in the minus or the plus state, can we just let the system decay out of that? You know, if I think that it's an atom system that's in some atomic state, just let it fall out of that state back into the ground state and get the photon. Is that an equivalent system instead of trying to put this onto the control pulse, onto the pi over 4 pulse?
Yeah, so if you're able to capture the emission from this two-level atom, I think that would work equally well. You could just wait until it decays spontaneously. You capture the fluorescence, and that's like extracting the energy from this engine. So that would work, I think, as well. That's, of course, it's an incoherent process. You may have to wait a long time for that photon to come out, but that would work.
I see.
Yeah, so that would affect, for example, the power of the engine or how rapidly you can operate it.
And then I can understand energy conservation in this case, just that in order to excite my original thing from the ground state to the psi state, I did have to put on some control fields that added energy into the atom.
Yeah, in order to make that measurement, you have to come along and do something, right? And so that process of doing something is energetically costly.
Yeah.
Good. All right, so let's go on to some other examples. So I want to give this a continuous example. And so this I'm coming back to this paper I published with Cyril. And the idea that we want to have is, let's go away from just a two-level system. Let's think about a continuous variable system. And I want to think about making some elementary quantum engines. So for example, I might want to make an elevator, but rather than lifting you or me up to the top floor of the building, I just want to lift a single atom up a few nanometers, for example. Or I might want to charge a battery. So if I have a battery and I want to charge it, I need to take electrons from, say, the plus side to the minus side. And I can do that by dragging an electron across a potential region of increasing potential. And so this is a kind of quantum engine I might want to think about creating using such kind of a quantum measurement powered version of this. Here's the challenge about this problem. I want to create this single atom elevator here. So I have my elevator platform. I have a counterweight. I have some pulleys. I want to lift this atom up some distance x. And the question is, can we use information about where the atom is to design an engine? So in other words, if I knew where the atom was, I would be able to tell if I'm pushing on this atom or not. Okay, so just like if you were on this platform and you jumped up, and I knew when you jumped up, in principle, then I could lift that platform while you're in the air without doing any work because I'm counterbalanced. Okay, so this is somehow the idea behind this engine. So let's think about this a little bit. So the atom of some mass is on the platform under the influence of gravity, little g. And we know from quantum mechanics that the wave function, let's think about it just being in the ground state of this linear potential with a hard wall edge. And we see that this ground state position wave function actually consists of a range of superposition of many positions near and far from this platform. So our strategy is we're going to try to detect whether the atom is near or far from this platform by, say, for example, shining a light or having some kind of optical detection, for example, with the transmission of some light, and be able to tell, is it close or far from this detector? So that's the idea. And we find two possible outcomes, let's say, that we can, if we find the atom is far away from the platform, it's not on the platform, so I can simply raise it up without doing any work, and then I'm able to effectively start over and at a higher position. So this is somehow the idea. We wait and we look and see if the atom is far away. If it is far away, we move the platform up, and then we've suddenly realized we're at a higher position. So I've essentially moved up this atom some distance h, and I've been able to do some work without actually doing any work. All right, so that's the idea. I've been able to extract work from this problem. But sometimes what you find is that when you look at this atom, you find the atom is close to the platform. What do you do then? Well, that's sort of a wasted thing. So at this point, our strategy is to wait. And eventually, the system will relax, kind of like we were talking about with Paul a minute ago. And then some photons will be released, and I go back eventually to my ground state if I wait long enough. Okay, so this is the basic strategy. So let's be a little bit more quantitative about that. We can solve this problem using a quantum bouncing ball type model, and we find that the eigenstates are area functions that are solutions of this problem. And there are some characteristic length scales and characteristic energy scales depending upon the force I'm applying by gravity and the mass of the particle and so on and so forth. Okay. So what we find is that when we do this analysis, we might say, Well, let's just make a very simpler kind of measurement. I'll make a projective in-out kind of measurement, where if the particle is less than epsilon away from the platform, that's one outcome, and if it's bigger than epsilon away from the platform, that's another outcome. Okay, so that's a two-outcome projective valued measurement. I introduce some projectors pi 0 and pi I to account for that, and then I can go through the analysis and do this kind of analysis. What I find, however, is this is a bad idea, because you can see that if you ask, for example, if I find it on the outside and you can ask what the post-measurement state is, well, the wave function would then be 0 from 0 to epsilon. It would take on this blue line here at epsilon and go like this. And if I calculate the energy of that state, because of this jump here, the energy is infinite. It diverges. And so in order to do this measurement, it would take an infinite amount of energy to actually carry out this scheme. And so this is it's a zero efficiency measurement, because I have to put in an infinite amount of energy in to do this measurement. So that's a bad idea. So let's do something more clever. And the more clever thing is that we're going to do is we're going to soften the measurement. We're going to put in some kind of gray region. So I still want a two-outcome measurement for simplicity, but this is a kind of continuous resulting two-outcome measurement. So formally, we can describe this with this positive operator value measure formalism measurement theory. And we're going to have two possible outcomes. And the idea is that I can define these measurement operators that are functions of position. And the two outcomes are the following. I want to interpolate, like I had before, like a projective value. So one would be 1 here and 0 here, but then I make it interpolate in the intermediate region. And the other is 0 from 0 to epsilon, 1 out here greater than epsilon plus W, but then takes on this more general softened version out here. So the interpretation is if I get outcome O, outside, O is for outside, then I know for sure it has to be bigger. The particle has to be farther away than epsilon from the origin. But it could be out here, but it might be here in this gray region. So the gray region between epsilon and epsilon plus W. And so I can write down this interpolation function there. All right, so what happens when I do this? Well, now I can run through some calculations. I can figure out some effective heat provided by the measurement, what we call quantum heat. And this is simply the amount of energy in the post-measurement state. Either if I have inside or outside, I can look at the expected energy of that state minus the energy I started with. And so then we can calculate that in this problem. And it turns out this so-called quantum heat only depends upon the value in the gray region between epsilon and epsilon plus W. And the work extracted, well, I know how much work extracted. It's very simple. It's just the amount of the difference, the height that I raise it. It's mgh, right, where h is now epsilon. Well, then times the probability I get the outside result and not the inside result. Okay, so I can calculate this work, this quantum heat, and I can define the efficiency of this engine as the ratio of this work to this quantum heat. And the reason the efficiency is less than 1 is because I usually have to waste some energy during this relaxation phase. If I fail, I have to let it, if I get squished, I have to let it unsquish, and then I lose energy in that relaxation phase. Okay, so what's part of this game then is trying to maximize the efficiency of this process. And one way I can do that is I can try to design my measurement just right so I waste as little energy as possible. And so the conditions that I want to have no energy wasted is the following. When I find the result outside, if I look at the post-measurement state, what I want that to be is I want to be that new ground state of the wall shifted by some distance epsilon in that new position. So I would like to have that exactly be my new ground state, so I don't have to waste energy that way. And similarly, if I get the fail result, if I find it inside, what I'd like is the post-measurement state there is nearly the same as the original ground state. And if I have that, then I don't waste any energy in this process in principle. And what we do is, if we do this calculation with that model I talked about before, what we want the epsilon to be a particular value in units of that characteristic length I was talking about for this problem to be about 1. And interestingly, we want the gray region to be very, very large. We'd like W to be very, very big, so I have a large gray region. And if you do that, here are the results here. So the displaced ground state is this red line in the new position, but the disturbed state with after outcome, it looks almost the same. It's a slight deviation at the top, slight deviation right there, but it's really, really good. And the outside measurement even looks better. It looks almost exactly the same as the initial state that I started with. Okay, so if I do that, then I can have almost perfect efficiency measurement engine. So here is the sort of results we find from this model. We're plotting the work, W, and the efficiency, eta. And what we see is a function, for example, of this value of epsilon. Here we're taking W, little w large. And so you find that the efficiency, so the efficiency is going to be maximized here at epsilon is around 1, and W is really large. That's that red region there. That's almost perfect efficiency. It's like something like 99.98 efficient. Whereas the work you see up here, actually, there's not much work out. I don't get very much work in that case. What I want is I want W small, and that gives me the maximum work. So there's this trade-off between work and efficiency like there is in normal thermodynamic engines. Indeed, if I plot the maximal along this dashed line, if I plot the work efficiency trade-off, you see it has this inverse kind of relationship here. Okay, so that's interesting. Let me say a few words about how you actually make this measurement. I talked about this weird two outcome measurement with sort of weird interpolation. How would you actually do that in the laboratory? So here's our proposal to how you might do that. You would design an interaction between the bouncing ball degree of freedom, say F. This operates on the particle degree of freedom, and you have a two-level system like a photon polarization or a spin of an electron represented by some polymatrix sigma y, and let's make it be an impulsive interaction. So it only happens at a very short time. And what you can see is that after this interaction takes place between this two-level meter, and the continuous degree of freedom, is that generates an entangled state like this. It looks like 0 times cosine of this function f I haven't defined yet, operating on the state phi, plus the qubit state 1 times the sine of this function f operating on state phi. So for example, if I choose f to be some phase ramp as a function of x, so it starts out at 0 phase, it increases linearly from epsilon to epsilon plus w, and then it stays up at pi over 2 after epsilon plus w. That phase ramp does exactly this generalized measurement, where if I get qubit state 0 or 1, that corresponds to this generalized measurement on the atom in the linear potential. So one other interesting thing we can do is we can do a sort of generalized energy analysis of this problem. This comes back to that point I was making earlier, that you don't generate energy from nothing. What you find is that you can look at the system, but also look at the energetics of the detector as well. And so you see generally you do work in this process by raising the atom. You waste heat by letting the atom relax. But what you find is that you also generally have to add energy to the detector as well in order to make the combined system be an energy conserving system. So what you find is that unless you energize your detector, unless you give energy to this two-level atom, this measurement will simply fail after a while. I won't be able to do the measurement anymore. So in order to make it work, I have to continually be re-energizing the meter that I'm doing this. So you can view this as a kind of a transfer then of energy from my meter degree of freedom to my system degree of freedom. So that saves the first law in this problem. Okay, let me switch gears now to a different version of this. And this is a paper we published just this year. And this is with my collaborators, Alexei Ofev, and also our friend and colleague, Kater Murch. who's working with us on trying to do some experiments on this kind of system. And what we did is we turned to a kind of 2-qubit version of this problem. And the 2-qubit version is interesting because it brings in this concept of entanglement. Once you go beyond a single degree of freedom, we have to worry about quantum entanglement, and that gives new features to this problem. So the model here is we have a two-level systems that are detuned from one another. Say one is blue and the other is red in terms of its energy. And the idea is we would like to be able to pull energy out of the system. And the way we do this is we allow these 2 qubits to interact via some flip-flop type interaction using a time-dependent coupling that couples the 2 qubits together with G, okay? Now, what do we do here? We start with the lower, this is a so-called red qubit. We'll start with that in an excited state, and we'll start with the blue qubit in a ground state, okay? So the whole energy of the system before I start is just this energy from the first qubit. When we can then turn on this interaction, we have to take into account the interaction energy that's generated there. But what happens if I just leave this interaction on, what happens is you'll get a swap operation. So this qubit will de-excite, this qubit will excite, and then we'll flip-flop back and forth indefinitely. That doesn't quite happen here because that would happen if they're completely on resonance with each other, because when they're detuned, you don't get a full transfer of the excitation from the red qubit to the blue qubit. It only goes sort of half or part way up before it starts to come down. So our strategy then is what we do is we wait in this system, in this cartoon here, we start in this situation here, we let it do this partial flip-flop where they're entangled now. But at point 2, what we do is now we do a local measurement of the energy of each of these qubits. So we look at the energy we measure in the local basis, the energetic basis here and here. And what you see is something interesting happens. If we time this right, we do wait our measurements. So there's a half a flop. Then almost always we find the left qubit is in the ground state and the upper qubit is in the excited state. But then you can say, wait a minute, how is that possible? Because I ended again with more energy than I started with. And the reason it's possible is because the quantum state at this point has a high overlap with this state and this state. And so what I can do now is, again, I can do the same trick I did before with a single qubit state. I can either apply a drive pulse to extract that blue energy, or I can again let it decay like Paul was saying and extract that energy like so, okay? And so what I end up with more energy than I started by the amount of the detuning I had. Now, it could be you might object, well, that only happens some of the time. Some other times I'm back in the original situation. I find this one is either red in the excited state, and this one is in the ground state. And it turns out because of the nature of the coupling, I can never have in this model up, up, or down, down. I only have down, up, or up, down, so to speak. And so you can go through this analysis and do the analysis of the interaction V between the 2 qubits. And what you find is that during the measurement process, I'm extracting energy from the correlations between the qubit in this measurement process. And so I can view this energy as coming from the correlation energy between the qubits as well as the measurement process itself. Okay. We can do the variations of this. So one of the variations is we make a chain of these qubits. And we can view this like a staircase. Imagine I have a bunch of qubits, each of slightly higher energy than the one before it. And I can simply do these swap operations one after the other, bringing the excitation to the next step in the staircase, and do the local measurements on each of these qubits. And in that process, what I can do is I can upconvert some original low energy qubit to some high energy qubit by stepping along this stair step. And what's interesting about this kind of proposal is that if I want to find a fixed gap from the beginning to the end, I can put more and more intermediate steps in between them such that the step size is smaller and smaller. And what you can find is that the probability of succeeding in that kind of arrangement becomes 1, because the closer they are in energy, you have this Zeno-like effect that the probability of achieving success becomes very, very close to 1 very, very rapidly. And so what I do here in these plots is I plot the success probability of going from here to here as a function of, for example, of the interaction strength G to the detuning delta as I increase the number of qubits. And you see I can very rapidly approach perfect success probability in this little scheme. So this is quite nice, I think. All right, let's go. So the other interesting thing about this process is you can look at the energetics of the process of measurement itself. You can say, okay, you can say do a measurement. What does that mean? So we have a model in the paper where we can bring along a little meter system here and have it couple, say, strongly to some other one of the qubits, say omega b, with some other coupling parameter chi. What's interesting is that as you make this measurement of process B, you can study the energetics of that process. And what happens is the entanglement between A and B gets destroyed. This is like this monogamy of entanglement. And I extract the energy of the correlation energy between the A and B, and I somehow transfer it. I transfer the correlations between B and my meter in the process of this measurement. So this is also very interesting. So this is the fuel of this entanglement powered engine that we can describe in terms of this measurement dynamic process as well. So this is like the measurement fuel, so to speak. Okay, how am I doing? So I've got about maybe 20 minutes left. Let me switch to another kind of engine we've talked about recently. And this is a kind of engine we're trying to build in the laboratory now. So you can think about on this upper picture here, something we call this classical Brownian engine. So suppose you had just a harmonic trap that was at some temperature T, and you had a bunch of atoms, or so you just even say one atom in that trap, and it was bouncing around according to some stochastic Brownian motion. What you could do is you could make an engine out of this classical process by coming along in a sort of Szilard engine type way and saying, where is the particle at time T? And in this cartoon, you say, aha, it's a little bit to the right. And what your daemon-like operation can do then is it can extract the energy of that particle by simply shifting the potential over a little bit. So you can imagine, suppose, for example, that this is a mass on a spring. The spring is undergoing some Brownian motion. If I find it to the right, I can simply hold the left end of the spring and pull it over towards the mass. So I relax the energy of the spring, and I can take energy out of the system that way. Okay, so I can pull work out of this process. So this is the classical version of that problem. And so you can do the thermodynamics of that and show that you can reach Carnot efficiency with that kind of engine. And so what we're interested to do here is we want to do a kind of quantum measurement version of that, where I replace the temperature T with just a quantum wave function. It could be in the ground state, or it could be as you like. It can be some higher excited states, or it can be some thermal state. And then we do some quantum measurements on this process. And what we did, you can do position measurements, or you could do momentum measurements, or actually what we do in this paper is we actually do both at the same time. We do this continuously, looking at both position and momentum in a continuous way. Now, why do we do that? First of all, why is it possible? Now, you learned in quantum mechanics class that it's impossible to make a joint measurement of position and momentum at the same time because they don't commute with each other. All right, but it's perfectly possible to make a measurement of first position and then momentum and then position, but you of course disturb the values you get in that process according to quantum mechanical laws. However, if you do this weakly, suppose you don't do a strong projective measurement of position or momentum, but I weakly measure position and momentum by coupling some meter to it that gives me partial information about the system, then it is possible to do joint continuous measurements of position and momentum, okay? And what you find is that rather than collapsing, for example, to a momentum eigenstate or a position eigenstate, the wave function itself is conflicted. It doesn't know which way to collapse. And so it actually undergoes some kind of random jitter in the quadrature variables. So if I look at some Husimi function picture or some Wigner function picture, what you'll find is that when you do this joint position and momentum measurement, I just kind of get diffusion in the x p plane, but I don't actually squeeze the wave function either in position or momentum. And that's what we wanted for this problem, is because if you squeeze it, remember I told you eventually we have to reset this engine. And if you squeeze it, it's not an easy way to unsqueeze this engine. And so that leads to inefficiency. So the easiest, most efficient way to do it is to not squeeze it in the first place. And so that's why we make this joint measurement of position and momentum. But then the same kind of classical procedure of feedback is the same. Once I find, I can use the information to infer the average position and momentum of this oscillator, and then I can then shift the origin of this potential to extract the energy. So here's a kind of cartoon of what it looks like. So we can do this using the formalism of continuous measurement system. So I like this. I work a lot on these continuous measurements. And so this is melding the formalism of these continuous measurements with this kind of quantum energetics point of view. And you can then track sort of in two ways. You can let this go for a while. So you can track the quantum trajectory of this oscillator in its quadrature space, and find eventually after a few seconds it's going to end up over here, and then I can then shift the origin of the potential to bring this guy back to the origin and extract that much energy in the process. Or the other way to do it is if I could do a kind of continuous feedback, where at every time step of my measurement, I get some kind of noisy measurement outcome, and then immediately apply the feedback to pull it back to the origin. And this is kind of a scatter plot of what you see when you do that kind of process. So you can apply the formalism of continuous measurement to calculate things like how much work does this engine produce, what's its efficiency, what's its power, because this is a continuous measurement process. The amount of work per unit time becomes very important. And what you see in these plots is you can predict the distribution of the work divided by the natural frequency of the oscillator as a function of work. And we have nice analytic and numerical expressions for these things. It's basically just a exponential decay curve here. And then I can also plot the how much work I get out if I wait a long time. So if the longer I wait, I can calculate the average work I extract as a function of time, again, analytically and numerically. And then you can also look at the power of the engine. Now, what's the work per unit time? Here I divide by the natural frequency, and it turns out that it's related to the strength of the measurement. So whenever you make these continuous measurements, there's a characteristic measurement time of collapse, which is the inverse measurement strength of the measurement. And so the amount of power I get is proportional to that measurement strength, and then also to the variance of the position or momentum in the initial state. Okay, and what you see is that this actually goes to a steady state as a function of time as you continue to do this measurement. So this is a nice continuous quantum measurement engine where we have very good control over the predictions of the engine performance. And again, if the efficiency, if you have this perfect equal strength position and momentum measurements, it's a perfect efficiency engine. Okay, I want to leave some time for questions, so maybe I'll go through this quickly. We also have some results about unread measurements. So far, most of the measurements are looking at the result and then doing some kind of feedback operation to extract the energy, but there are ways of doing it without looking at the results of the measurement. And the idea there is you use the measurement process as a kind of hot bath. It gives energy to the system. And so there are ways of doing a kind of auto-like cycle where I have adiabatic compression and expansion and then measurement to be able to extract energy. And then you have a auto-like engine kind of efficiencies in these problems. We have another kind of single qubit engine using a four-stroke engine, where you do you replace the compression and expansion with some coherent rotation. So this is using coherent resources rather than thermal resources. So we would do some kind of coherent rotation, and then this is a four-stroke cycle where I go rotate, and then I do a readout along the plus minus basis for stroke 3, for stroke 2. I rotate back for stroke 3, and then I thermalize for stroke 4. And then you can show that this engine actually approaches ideal efficiency in this kind of process. And yeah, so here are some results of that engine. Again, you see efficiencies approaching 1 for a particular value of the rotation angle. Okay, but again, there's a trade-off with work there, just like in thermodynamics. Okay, so I think I'm going to end here, and I leave plenty of time for questions. So I discussed this new kind of quantum engine. It's powered by the fluctuations of measurement, and I've showed how under certain conditions you can use the information in the measurement to rectify those fluctuations and pull this energy out of the problem. Even things like in this oscillator engine, you can think about the measurement process is essentially like putting a quantum of heat or quantum of noise in the system. We show how to pull that quantum of noise back out of the system. And then we talked about these different examples. And what's cool about them is that there's no thermal baths. So in principle, you can have perfectly efficient measurements, engines with these types of engines. Okay, so I'm done.
Thank you so much. Clap, clap, clap. So I have a question to get things started. So when you were talking about the harmonic oscillator engine, you mentioned, I think there was ongoing experimental efforts too, and I saw Gator on that paper. Can you say more about how you're realizing that experimentally?
Yes, so that's a really good question. And so we have different ideas. So the idea is that we're trying to use electrical oscillator for the harmonic oscillator, and then trying to do optical readout. So the idea is that you would have some kind of microwave controlled tone that dispersively interacts with the dipole moment of this oscillator, and then you can do some kind of phase sensitive or phase preserving measurements to pull out the two quadratures of that measurement. So that's one idea we're playing with. So we're trying to do that. And so there's another experiment done by Irfan Siddiqui where he did a joint non-commuting measurement of a qubit of looking at the two Pauli basis measurements by using two different cavity modes to do that. And so that's something we're also thinking about for doing that. And we're also working with Cater to try to do this version of the entanglement engine, where you try to then create entanglement between two qubits and then trying to do local readouts. And we're trying to do that by maybe making a quick coupling to a very strong relaxation channel to pull photons out of that qubit. So those are some of the experimental efforts we're pursuing.
Let's see, any other questions? So are you aware of other experimental efforts taking these ideas besides the ones you just mentioned, especially the entanglement engine, I guess, makes me think
of this is part of the fun of doing physics, is that when you publish these things, sometimes people pay attention and notice. And so we've had, I think, two other groups approach us, I think one Chinese group and one European group, interested to try to do this as well. So the Chinese group wants to do it with photons. And so they want to have a sort of photonic version of this 2-qubit entanglement measurement engine. And so that's fun. And so we're talking with them. Yeah, so I think people are getting interested.
Awesome. Yeah, so I had a question from one of my students in my quantum mechanics class very recently that I think I was not able to answer very cleanly, and I think basically you gave me the answer with this talk. So thanks for that.
Excellent. Okay.
Yeah.
So Andrew, I have another kind of a general question. So typically, and I'm sorry if I kind of missed this if you already said it, but typically, of course, with classical thermodynamics, we're trading off, we're sucking entropy out of the reservoirs, and that's what's doing the work. And in your case now, when you have entanglement, of course, if you look at only one of the subsystems, then there's a lot of entropy. And I'm wondering if somehow that the underlying principle is the same, therefore, in the two different approaches, where it still is somehow an entropy resource that's being used.
Yeah, we have these discussions of entropy in our papers. I didn't want to go into them because it's a bit technical, but that's basically right. You can look at somehow an entropic resource, and if you view it as you have complete knowledge of the entire system, then of course it's a very ordered state, right? But you have to have both parties talking to each other to know about this order. Right. But if you only have one of the parties trying to do measurements without communication, then it becomes very disordered. Right. And so, yeah, and so that certainly plays a role there. Yeah.
And is there then also the analogy of of like the free energy, where, you know, if you have a finite reservoir, there's only so much energy only so much work you can extract from it. I guess in your case, you know, when you're considering your reservoir to be quantum systems, it's kind of automatically in that same space.
Yeah, I mean, we're able to get around a lot. I mean, so there's sort of a debate about how you think about this. So some people say you should think about the quantum measurement as like a thermal reservoir with infinite temperature. Or some people say, no, you should think about a quantum measurement as a thermal reservoir with zero temperature. And I say, no, just don't think of it as a thermal reservoir at all. It's a quantum measurement. It's something very different. It's not a thermal reservoir. But from this point of view, you can get around many of these thermodynamic type things. There are analogous phenomena, but there's a different kind of class of effects.
Yeah, interesting.
Great. Okay, so there's no